Hello, I'm Rohit Chadha, and I'm going to speak about a paper on deciding accuracy of differential privacy schemes. This is joint work with Gilles Barthe, Paul Krogmeier, Prasad Sistla, and Mahesh Viswanathan. Essentially, differential privacy is a technique that is used to answer queries to databases that may contain private information. What we want to do is to allow data analysts and policymakers to query databases without compromising privacy of individuals. This proves to be a hard problem. A celebrated result of Dinur and Nissim says that the entire information of the database can be revealed with a small number of queries. In the differential privacy framework, what we do is we actually trade accuracy for privacy. So a differential privacy mechanism typically mediates the exchange between the database and the data analyst. When the database is queried, the mechanism adds some random noise to the true answer before forwarding the answer to the data analyst. So the data analyst gets slightly inaccurate answer. The random noise added depends upon the parameter on a parameter epsilon, which is called the privacy budget in differential privacy literature. And typically smaller epsilon means better privacy but more inaccuracy. So differential privacy has a nice definition, which we have reproduced here. Uh, and actually, we had studied the problem of verifying differential privacy in our LICS 2020 paper. And what we had shown was that the problem of verifying differential privacy is in general undecidable. Uh, and we had also identified a class of program which we call difffile, for which this problem became decidable. Okay, so in this paper, what we are focusing on is the problem of verifying accuracy of differential privacy. So the natural question to ask is, what is accuracy? So here is where we encountered our first stumbling block, and that is, unlike differential privacy, there is no uniform definition of accuracy of differential privacy mechanisms. Instead, individual differential privacy mechanisms have accuracy claims that are specific to the mechanisms. Mostly what we found was that they are stated as having a low probability of error. And you can imagine that we can use other measures such as standard deviation or root mean square error. On the other hand, in this paper, we will just focus on accuracy that is stated in terms of having a low probability of inaccurate answers. And for the rest of this talk, we will just assume that a differential privacy mechanism is nothing but a randomized program. So if you have a randomized program, so a natural starting place for defining accuracy would be to look at the standard randomized algorithms literature. And in this literature, accuracy is typically stated in terms of two parameters, which we call gamma and beta here. Assume that the randomized algorithm P is implementing a deterministic function det P. And typically what we say is P is accurate if for any input X, P outputs a value that is at most gamma away from the one output by det P with probability 1 minus beta. So of course we are assuming some sort of a distance function on the output space. However, what we found was that this definition does not serve our purposes for differential privacy. To illustrate this, let's consider a differential privacy mechanism, which is the sparse vector technique, also called SVT in short. Okay, and what we are giving here is a simplified version of SVT. So what SVT does is it takes as input an array of queries and implements the deterministic function det_p that determines the first index that is above a threshold t. Okay, and it wants to do it in a differentially private manner. So what it does is it starts by adding some random noise to the threshold, uh, then it scans the array from left to right, adding random noise to the array elements. As long as the noisy array element that's being scanned is less than the noisy threshold, it outputs bottom. The first time the noisy array element that's being scanned is above the noisy threshold, you actually output top and quit. Okay. As I said before, this is a simplified SVT. In general, SVT can output C elements above noisy threshold. The noise itself that you can see here is taken from a special distribution called Laplace distribution. So this is what the Laplace distribution looks like. As you can see, it is symmetric around its mean mu. This is pretty much like the normal distribution, which is also symmetric around its mean mu. It has a parameter a in addition to the mean mu, and what you can see is that this parameter a decides its peak. Larger a means bigger peak and hence more concentrated around its mean. So from this PDF or this picture of the PDF, what we can conclude is that the probability of getting the correct answer to SVT will depend upon how close the queries in the input array are to the threshold. So if the queries are really close, the probability of inaccuracy is going to increase. If the queries are far away from the threshold, then the probability of getting the correct answer will increase. The formal statement of accuracy is something like this. If the relevant queries in the input array are at least alpha away from the threshold t, then the SVT outputs the correct answer with probability 1 minus beta, where beta is given here, but given by this expression here, 2n e to the minus alpha epsilon by 8. I would like to highlight here that we have a new parameter alpha, also that beta is a function of alpha and epsilon. Further note that beta involves the Euler constant E, and actually it's very common to encounter the Euler constant in differential privacy literature, including the definition of differential privacy. Okay, so what we saw was that this situation with SVT repeated for other examples also, and that for DP mechanisms you also need to consider distance function on the set of inputs, which we call DIN. And our observation is that basically if the input u is very close to a set of inputs for which det_p gives a different result than u, so in some sense the set of elements which disagree with u, then the probability of inaccuracy tends to increase. On the other hand, if u is far away from the set of disagreement, then the probability of getting an approximately correct answer increases. So in SVT, for example, close to threshold means that a small change in input would result in a different correct answer, and far away from threshold means that a large change in the input is needed to get a different correct answer. So this distance to disagreement, which is basically distance of an element u to the set of disagreeing inputs, is an important concept for us, and we will call this distance to be distance to disagreement and denote it with dd of u. Okay, and we also assume a distance function on the set of outputs. Okay, so we are ready to define accuracy. We have three parameters in the definition of accuracy: alpha, beta, and gamma. And what we say is that a DP mechanism or differential privacy mechanism P is alpha, beta, gamma accurate for input U if whenever U is at least alpha away from the set of disagreeing inputs, or when the distance to disagreement of U is at least alpha, then the probability that P outputs a value that is gamma close to the correct answer is at least 1 minus beta. Further, the DP mechanism is alpha, beta, gamma accurate if it's accurate at all inputs. So if we were to apply this definition to accuracy, we can restate the accuracy statement that we saw for SVT in this framework as follows. The distance on the set of inputs can be taken to be the usual L infinity norm, that is distance between two input arrays of the same length can be taken to be the maximum of the absolute value of difference at each index. For output distance function, two outputs are said to be at distance 0 if and only if they are the same. If the two outputs are different, then you can take virtually anything for the distance. For example, what we did in our paper was to take it to be infinity. Now what we can show that the accuracy claim for SVT that we encountered before is equivalent to saying that SVT is alpha, beta, 0 accurate for beta given by this expression 2n e to the minus alpha epsilon by 8. Okay. And in fact what we did was we looked at several DP mechanisms and were able to show that the known individual accuracy claims for these mechanisms can be recast using our proposed definition. So what we looked at was Laplace mechanism, exponential mechanism, SVT, noisy max, numeric sparse, and small dB. And what's notable here is numeric sparse, for which we needed all three parameters. In fact, for numeric sparse, we also showed that we were able to improve on the known accuracy claim, that is, improve the error probability by a factor of almost 2. So having obtained a uniform definition of accuracy, we studied the decision problem of verifying accuracy. So let's set up the verification problems. Assume we are given a differential privacy program P, an interval I of possible privacy budgets epsilon. Okay, so what you are going to assume is P is also parameterized by the privacy budget epsilon. We're also given a deterministic program det P, okay, an input distance function d subscript n in, and an output distance function d subscript out, and a function eta which we will call admissible region, that basically given the privacy budget epsilon and an input u to P gives the set of possible alpha, beta, and gamma. Okay, so what we note here is that eta is a function of epsilon and u. So alpha, beta, and gamma depend upon epsilon and u, and in fact they can also depend upon each other. It's just like as we saw for SVT. We consider two decision problems. First is accuracy at an input, that basically given an input u determines if P is alpha, beta, gamma accurate at u for all possible privacy budgets and for all possible values of alpha, beta, and gamma. And the second problem that we consider is accuracy at all inputs, that determines if P is alpha beta accurate for all inputs U, for all possible privacy budgets, and for all possible values of alpha, beta, and gamma. Like the problem of checking differential privacy, both decision problems turn out to be undecidable for general randomized programs. So natural question to ask is whether there is a useful class of programs for which the accuracy problems become decidable. Okay. And the answer is going to be yes. We just highlight some of the challenges that need to be overcome for uh, decidability. So remember, differential privacy programs are parameterized by a privacy budget. So a program is really a class of programs, one for each possible value of epsilon. It can contain integer and real variables, which results in potentially uncountable set of states. Uh, Further, we need to compute for each input I the probability of obtaining an output that is close to the correct output when the program is run on the input I. And of course, this probability is going to depend upon the privacy budget. So the natural place to look for the class of programs is to look at different programs for which we showed that differential privacy decidable in our LIX 2020 paper. So programs in difffile plus may have four kind of variables: integer valued, real valued, boolean valued, and variables that take values from a finite domains. We're only going to consider programs with a finite number of variables. So in this language, the infinite domain variables, that is the real and integer variables, cannot be assigned inside loops. There is no restriction to assignment to domain and Boolean variables. Real variables can be assigned values from Laplace distribution, and integer variables can be assigned values sampled from discrete Laplace distribution. Only domain and real variables can be used as input and output variables in difffile plus. In difffile, we only allow domain variables to be used as input variables. So really the main difference from difffile is actually that we allow real variables to be also used as input and output variables. So our first uh, result is that both the decision problems for accuracy at an input and accuracy at all inputs are decidable for difffile plus programs, assuming that Schanuel's conjecture is true. Schanuel's conjecture is an open problem in transcendental number theory. Essentially, what we showed was that the two verification problems reduced to the problem of checking validity of first order sentence in the theory of reals with the exponential function. The decidability of checking validity of a sentence in the theory of reals with exponential function is a long-standing open problem. And this is where Schanuel's conjecture comes in, because it was shown by McIntyre and Wilke in 1996 that if you assume that Schanuel's conjecture is true, then the validity problem becomes decidable. So we sketch here the proof idea behind this result. Essentially what we show is that the semantics of a difffile plus program can be given as a finite state DTMC parameterized by the privacy budget epsilon and the initial values of real input variables. For in this DTMC, the transition probabilities, which again depend upon epsilon and the initial values of input variables, of real input variables, uh, those transition probabilities we showed can be defined in first order theory of reals with exponential function. So a consequence of this DTMC semantics is that if a program has only domain valued outputs, then given an output O, the probability of P outputting O on a parametric input I can be defined in the first order theory of reals with exponential function. This gives the result for programs with only domain outputs. For programs with real output variables, what we can show is that verifying accuracy for such programs is equivalent to checking accuracy for a different program with only domain output variables. We also have some unconditional decidability results, namely results in which we don't need to assume Schanuel's conjecture, and we highlight here the main one amongst them. What we show here is that the problem of checking accuracy at an input is unconditionally decidable for diff-while plus programs when gamma is taken to be a fixed rational number. Essentially, in this case, what happens is that the first order sentence that we get lies in a fragment for which the validity problem is decidable. As a corollary of this result, what we get is that the decision problem's accuracy at input and accuracy at all inputs, both of them, are decidable for diff-while programs as their input and output variables take values only from a finite domain, and hence there are only a finite number of interesting gamma to consider. For implementation of these decision procedures, since a general decision procedure is subject to Schanuel's conjecture being true, we can only aim for accuracy at an input for a fixed gamma. So this decision procedure is implemented in a tool called DIPSI Plus. DIPSI Plus builds on DIPSI tool that we built in our LIX paper. Because it builds upon DIPSI tool, it inherits its restrictions, such as it only allows for loop-free programs and only a domain input and output variables. Okay. Note, just having only domain input and output variables still allows us to cover to verify accuracy at an input for programs with real variables, as we just saw that the accuracy for such programs is equivalent to checking accuracy for programs with domain output variables. So what DIPSI Plus does is it checks for alpha, beta, gamma accuracy at an input for a given input program P for all possible epsilon. Okay, and what we do is, instead of verifying accuracy at a single input, we give an integer range for input variables. Thus, we verify accuracy for a set of inputs. The deterministic function that P is given as a table. For each possible input, we give the expected output of det P in this table. Gamma is taken to be an integer, and for many examples, like in SVT, the only possible value of gamma is 0. Okay. Beta itself is given as a function alpha and epsilon, and for each u, what we do is we just choose alpha to be the distance to disagreement in the experiments, and so that means that we actually verify accuracy for all possible values of alpha, beta, and gamma for this input. So we actually do verify accuracy at an input. Okay. And DIPSI Plus, the way it works, it generates a Mathematica script The script generates and checks the validity of the first order sentence modeling accuracy. We evaluated diffc plus on several examples such as SVT, noisy max, Laplace, and numeric sparse with small input arrays. We were able to verify the accuracy claims for these mechanisms. In fact, we were also able to verify accuracy claims with smaller beta than known in literature. This suggests that the known accuracy bounds can possibly be improved. Finally, we observed that uh, verifying accuracy is faster than verifying differential privacy, since in verification of accuracy we only have to compute the probability of obtaining one output, namely the output of det p on the given input. For differential privacy, on the other hand, we need to compute this probability for each possible output. Detailed experimental results are in the paper. Here we just show the running times for the simplified SVT that we discussed earlier. The first column here gives the number of array elements, and the second column here gives the time of generating and executing the Mathematica script. As you can see, generating Mathematica script takes no time, and all the time is really in executing the Mathematica script. Each array element here can, in this experiment, can take a value -1, 0, or 1. So thus an experiment with n array element verifies accuracy for 3 to the n possible inputs. To conclude, we gave a uniform definition of accuracy which applies to accuracy statements for several differential privacy schemes that we encountered in literature. Showed that the problem of verifying accuracy is in general undecidable. We also identified a class of programs, diffile plus, for which the problem of checking accuracy becomes decidable assuming Schanuel's conjecture is true. Diffile plus extends diffile from our Lix paper by allowing real input and real output variables. We also showed that accuracy is decidable for diffile programs without assuming Schanuel's conjecture. So essentially programs that have only finite domain input variables and finite domain output variables. We have implemented our decision procedure for checking accuracy at a given input in a tool DIPC plus, and we have verified accuracy claims for several DP differential privacy mechanisms with this tool. Thank you.